theories of parallel-combinable processes with this card.
So this is a work done by Brendan and me. So first I would like to start with some background. This is an existing mathematical framework that we're working on. There are currently more than one definition of what are resource. There are many ways of talking about resource theory, but the one we're working on is the one defined by Bob seconds. And well, the motivation for the core concept of this framework is, first of all, transformations of physical state to another. But we want to also think about transformations between, more specifically, for the theory, from one resource to another. So one thinks of what can be considered as a resource, when one can be transformed into another. And so, like an intuition, can be considered as a fact of intuition, that if you can transform one resource to another, A to B and B to C, then you can transform A to C. And this is modeled by a pre-order relation. And for the ability to combine, to create new ones, new states or new resources from existing ones, can be modeled in a monoid, or is modeled by a monoid in this theory. So both structures put together define the pre-order monoid, which is one of the core concepts in this mathematical formalism. So one can always get pre-order monoid from an existing category by deep categorification, but I can use a theorem for it. I'll skip it and I'll give you a more simple explanation of how to do it in 1 minute. So the other concept needed for this framework of reason theories is the concept of free processes. So basically, processes are have very low costs or almost no cost to perform. And this is modeled in this theory. So now we've moved to categories. First I started with pre-order monoid. Now I'm moving on to category theory, and I'll show you in a minute how to go back to how given symmetric monoidal categories one can get a pre-order monoid. So free processes are modeled by a pair of category and subcategory. The subcategory representing free processes. And examples of these, very simple examples of these, would be bijections being the full all object including subcategory of the category of sets, and same thing with injections. I write here this cup to represent, to say that the categorical tensor is the categorical product is a disjoint union, as opposed to these ones where it is the Cartesian product. Now moving on to our results in the paper is that there's a relation defined in this framework, which stands for can be transformed into. So the ability of one process being able to be transformed to another. And what we did is we found the consistent, complete family of consistent pricing functions. So basically, a function into the reals that is essentially consistent. And also we find we give a theorem that can be used in a more general way when trying to come up with these consistent pricing functions into the reals. This can be considered value in the sense that reals are they're kind of easy to understand, right? It's, assigning a cost to something is and getting a real number out of it is can be considered valuable. So that's why we came up with this tool to make life easier when trying to come up with these complete families of pricing functions to the reals. And in this theory, in this framework, in the recent theory framework, these are called complete family of monotones. And well, a monotone would be a monoid homomorphism that preserves the order, so order preserving homomorphism into the reals. And okay, yes, I just added that note to my knowledge. This hasn't been worked out, so hopefully this theory, or possibly this theory, could help ease the task of coming up with these complete families. So the relation that is defined in these categories is this one. And just to make it easy to understand, so we say that these two morphisms are related. You can say this one is greater than or equal to this one. Whenever we have free processes, these two, either one of the two free processes, and J can be the arbitrary morphism. So when these two are free, when there exist two free morphisms such that this quality holds. So this is the definition for this relation, this categorical assessment. And to get the pre-order monoid, what we do is that we do a decategorification into a pre-order monoid where the order the order holds whenever there exists such free morphisms. And the monoid structure is given by the tensor. So yeah, so what we worked out in the paper are this complete family of monotones, which basically reflect the order back. So they call if. So concretely, for this resource theory, we have sets as the main category and projections as the subcategory. So projections are morphisms are projections. The complete family of monotones is given by, this is something could be explained much easier if I just show you the example. So for this very simple example, what we do is that we come up with, we basically can think of this as an array of stars in 2 to the infinite to the left, and we basically write the instance multiset value, as it were. So for f, for row f, we have value 2. So this is a instance of value 2, this is an instance of value 3, and this is an instance of value 3. So we have 2 3s and 1 2. So that's what we write here. And the rest are 0, right? And for G, we only have an instance value 3. So we have 1 to the value 3. So what we do is that we compare these values, and they will be greater than or equal. And that's that's the condition that gives us the calculation. So this will be worked out. But this is just a counter example, and it doesn't hold. So if you have 3 and 4, so 0 is not greater than or equal to 1. So this doesn't hold. So these two, it is not the case that f greater than or equal to g. And for injections, it's very similar. But for injections, what we have is, I wouldn't call it majorization, but it looks a little bit like majorization because one must add all the values greater than or equal to the left. So for here, I assume, well, all of these are 0, right? 5, 6, 7, because it's just a finite set, and we will only have 3, 3, 2. So we have 2 3s and 1 2 for f, and for g we have 1 2 and 1 3. So 1 2 1 3. But this condition, the condition is that all the we need to keep on adding, and from the left, so we order these. So they're ordered, right? 2, 3, 4 to the infinite, and we add. So this is a little bit like majorization, and that's the condition for injections. So for the general theorem, so why is this theorem of value? Is because so coming up with one monotone for a reset theory is relatively easy. So if you do the for injections sets, for finite sets, this is actually a valid monotone. So it's very easy. You think about this kind of intuitive, isn't it? Sorry. So this is actually one monotone, but as I mentioned before, getting many of these actually turns out to be harder. And so far I'm just working with these really easy categories, right? So this is actually harder to come up with more than one. And finding even one monotone that satisfies if and only if condition is much harder. And finding all possible monotones, which is what this theorem does. That satisfy the if and only if condition is much harder. So our theorem, what it does is that it simplifies the task to only identify these 3 properties for all free morphisms. So I'm just going to go back. So if you recall from the graph diagram that we have, we just need to find the existence of eta 1 and 2. But this theorem says, well, for all of these, we just need to find that these 3 properties hold for that particular monotone. So here's the actual theorem, which is harder to read. That's why I gave this. I just reduced it to explain these 3. Lastly, so future work, working with more with different categories, more fiscally oriented, and extended theory, so you can also include being able to measure some properties of interest. Just to give one example, if one takes category stochastic matrices as the main category, it is with this Wurster theory framework, it's currently not possible to measure say irreducibility, namely because irreducible matrices don't form a category, they're not closed on the composition, and irreversibility, mainly because the identity is reversible. So that would be the outlook for future work.
Are there any questions, comments for Hugo? Yes?
I have one. So if I understood well, so in one of the previous slides you defined the mu in your monotone, right?
Yeah.
So here, exactly that one, you are the property number one, you are requiring that mu is act as a product. So on product of the tensor product morphism, mu acts as a product.
Yeah.
So in I was thinking about quantum theory, and in a similar case we require additivity instead of it. So
Yes.
is there any particular reason why you
This is
require
actually-
this product form instead
sorry.
of class form?
Yeah, this is not this is not actually the product, it's just the monoid operations.
Ah, okay.
Which, yes, you're right, it is additivity.
Because I was thinking of the product in R since they are.
Yes.
This can be anything.
Okay. That's fine.
Yes?
Just a comment. I think this talk proved that this screen is not totally useless because we finally use this project screen. All of these people actually they gave talk before. Use this screen. So
Okay.
yeah.
Okay, that's good. Okay. Any more questions, comments? Then thank you. I take the opportunity to thank Jamie